At time t seconds, where t is greater than or equal to 0, a particle p moves so that its velocity v meters per second is given by v equals 6ti minus 5t to the power of 3 over 2 j. When t is equal to 0, the position vector of p is minus 20i plus 20j meters. And part A wants us to find the acceleration of p when t is equal to 4. So first of all, if we find some way to link velocity and acceleration, this would be a good start because we have an expression for velocity up here and our answer is to do with acceleration. We want to find the acceleration of p. So as a general rule, we know that velocity is equal to the integral of acceleration. And therefore, if we reverse that, acceleration is equal to the derivative of velocity, so dv by dt. So if we went to find this, we would want to differentiate this expression up here. And so for 6t, we do the coefficient of t, which is 6, multiplied by the power, which is 1. So 6 multiplied by 1, and then we take away 1 from the power. So we're left with 6t to the power of 0, which is just 6. And then we keep the I just constant. We don't do anything to the I and the j. And then we do the exact same to the next term. So this becomes minus 15 over 2t to the power of a half j. And now we have our expression for the acceleration. But the question's not asking for a general expression for acceleration. It's asking specifically when t is equal to 4. So if we want to find the acceleration at t equals 4, we just substitute in t equals 4 into our equation. So we have a is equal to 6i minus 15 over 2 multiplied by 4 to the power of a half j. And this turns to acceleration is equal to 6i minus 15j meters per second, because remember it is acceleration, so we do give units, and that's the question. So the 3 marks for this question, the first 2 actually come from differentiating, because we get a method mark just for knowing to differentiate v, and we get a further answer mark for differentiating correctly. So this would give us 2 marks as we've differentiated and we've got the right numbers. And then we get our last answer mark for actually getting that the acceleration is 6i minus 15j meters per second squared. Now part B wants us to find the position vector of p when t is equal to 4. And position vector is to do with distance, or we could call displacement. And the relationship between velocity and displacement is that velocity is the derivative of displacement. So v is equal to ds, we denote displacement with an s, ds by dt as a general rule. So therefore, displacement is the integral of velocity. So if we were to find the displacement, which is what we'd need to do to find the position vector, we would integrate the expression for velocity, which is 6ti minus 5t to the power 3 over 2 j. And we would integrate this. And when we integrate things to do with I and j, we leave the I and the j alone, just as we did for part A with the differentiation. So first of all, for 6t, we add 1 onto the power and divide the 6 by it. So 6 divided by 2 is 3t and then squared I. And then same for the next one, adding 1 to the power. So 5 divided by 5 over 2 gives us 2t to the power of 5 over 2j. And then because this is integration, we need a plus c. But the difference with integrating vectors is that the c is also a vector. And when we find what c is, which is what we're going to need to do in a minute, c will have an I and a j term involved with it. So now we have this expression for the position vector of P, but we don't know what C is, and that's what we need to find now. So if we go back to the question, we're told that when T is 0, the position vector is minus 20i plus 20j. And given that this is our expression for position vector of P, we can substitute in T equals 0 to try and find C. So at T equals 0, we know that this whole expression should equal minus 20i plus 20j, because that's what we were told in the question. And because this term here and this term here are all multiplied by 0, we get that C is equal to minus 20i plus 20j. Now, if we include that in our original expression, but we substitute in that C is equal to minus 20i plus 20j, and if we factorise them by the I and the j terms, just to make it easier, we have 3t squared I minus 20i. So if we write this as 3t squared minus 20i, and then do the exact same thing for j. So we have plus 20 minus 2t to the power of 5 over 2j. We now have our full expression for displacement, or the position vector. Now again, we want to find the position vector at t equals 4. So if we substitute this into our expression at t equals 4, we get that this is equal to 3 multiplied by 4 squared minus 20i plus 20 take away 2 multiplied by 4 to the power of 5 over 2j. And when we put this into a calculator or work it out, we find that the displacement, and therefore the position vector of P at the point t equals 4, is 28i minus 44j. And this is all in meters, because again, we're measuring a direction displacement, which is measured in meters. Now, this question was also 3 marks, and our first mark came from integrating the equation for velocity, which we've done up here, and then we got a further answer mark for doing this correctly and getting the right numbers, the numbers they have in the mark scheme. And then last of all, we get an answer mark for actually finding that the position vector at t equals 4 is 28i minus 44j meters. A particle P moves with constant acceleration 2i minus 3j meters per second squared. At time t equals 0, the particle is at the point A and is moving with velocity minus I plus 4j meters per second. At time t equals capital T seconds, P is moving in the direction of vector 3i minus 4j. Part A wants us to find the value of t. So the first thing we want to do for this question is find an expression for the velocity of P. And the reason for this is because we're told at time capital T seconds, P is moving in the direction of this vector 3i minus 4j. And what this means is that it's parallel to this vector, and this means that its velocity is some multiple of 3i minus 4j. It doesn't have to be exactly 3i minus 4j, but it has to be some multiple of it because it's moving parallel. That's just a general rule with vectors. So to find the velocity of the particle P, and we've got the expression for acceleration, we know as a general rule that the acceleration of particle P is equal to the derivative of the velocity. And therefore, if we reverse this, we know that velocity must be the integral of acceleration, which is 2i minus 3j, and then this is dt. So if we were to integrate, we can just write this as 2ti minus 3tj, because if we treat 2i as 2t to the power of 0, we add 1 to the power, so we get 2t to the power of 1, and then divide the coefficient of t, which is 2, by this power. 2 divided by 1 is 2, so we're left with 2t. And we do the exact same thing for minus 3j, and we get minus 3tj. And then because this is indefinite integration, we have to add a constant plus c, which in this case is also a vector. So now we want to find what c is, so we can get a complete expression for velocity, because this isn't quite complete because we don't know what c is. To find c, we can use some more information we're told in the question, which is that at time t equals 0, the particle is moving with velocity minus I plus 4j meters per second. So we can say that when time is equal to 0, this expression here, so where we replace t with 0, should be equal to minus I plus 4j. And given that this term here and this term here both go to 0 because they're all multiplied by 0, we know that c is equal to minus I plus 4j. And therefore, if we were to write the full expression for velocity, and if we also factorize the I terms and the j terms just to kind of keep them together, because it tends to be easier to work with them like that, we get that 2t minus 1I plus 4 minus 3tj is our expression for the velocity of particle p. So now we have this complete expression. We know that at time t equals capital T seconds, p is moving in the direction of the vector 3i minus 4j. And in the direction implies, as I said previously, that it's parallel. And given that parallel means that it has to be a multiple of this vector 3i minus 4j, we can write this as lambda, where lambda is just an unknown that we need to work out, multiplied by this, which we can then expand to 3 lambda I minus 4 lambda j. And therefore, if we say that at time t equals capital T seconds, the velocity is equal to this 3 lambda I minus 4 lambda j, we can actually solve for t. So if we say that when t is equal to capital T, and then we write out this whole expression, but we replace t with capital T, and then this is all equal to 3 lambda I minus 4 lambda j. Now what we know now is that we can do something called comparing coefficients, which is that the coefficient of I on the left hand side, 2t minus I, has to be equal to the coefficient of I on the right hand side, which is 3 lambda, and it's the exact same for j, so 4 minus 3t has to be equal to minus 4 lambda. So if we write out these two expressions, we can actually solve to find t. So if 2t minus 1 has to be equal to 3 lambda, and 4 minus 3t has to be equal to minus 4 lambda, if we rearrange both of these, where lambda is the subject, so over with this one, we have that lambda is equal to 2t minus 1 divided by 3, if we just divide both sides by 3, and here lambda is equal to minus 4 minus 3t all over 4, if we divide by minus 4, we now have two expressions that both have lambda equals at the start of them, which means that we can set, if we call this equation 1 and this equation 2, we can set equation 1 equal to equation 2. So if 2t minus 1 is equal, divided by 3, is equal to minus, and if we expand out this bracket on the top, minus 4 plus 3t divided by 4, if we multiply both sides by 4 and then multiply both sides by 3 to get rid of these two denominators, we're left with 4 bracket 2t minus 1 is equal to 3 bracket minus 4 plus 3t, and when we expand these out, we're left with 8t minus 4 is equal to minus 12 plus 9t. And now if we take away 8t from both sides and add 12 to both sides, we get that t is equal to 8. And that's our answer. And there are 4 marks available for this question. Mark number 1 is a method mark, and it comes from finding this first expression for velocity that involves a c term. And then we get an answer mark for finding this c term, and therefore stating that this over here is the whole expression for velocity, 2t minus 1i plus 4 minus 3tj. And then we get a method mark for doing this equation over here, so we find both equations in terms of lambda and set them equal to each other as a simultaneous equation. It gets us a method mark. And finally, we get an answer mark for finding that t is equal to 8. At time t equals 4 seconds, p is at the point B. Part B wants us to find the distance AB. So because we wanted to find the distance, this means that we know we're talking in terms of displacement. And the general rule with displacement is that velocity is equal to the derivative of displacement. And we have an expression for velocity that we found in part A, which means we can find displacement. So if we reverse this, it means that displacement is equal to the integral of velocity. And our expression for velocity was 2t minus 1i plus 4 minus 3tj dt. And if we integrate this, we get that this is equal to t squared, because we add 1 to the power, and then we divide the coefficient of t by that power. 2 divided by 2 is 1, so we have t squared. And then we use that exact same method for all of the other numbers, and we're left with this. And we have to remember that there is a constant vector that we can call d, just because we used c in the previous part, that we have to add on. However, if we assume, we're told earlier, we were told that point A is when t is equal to 0. And if we make the assumption that therefore displacement is also equal to 0 at this point, it makes the calculation a bit easier. And that means that if when t is equal to 0, s is equal to 0, then if we substitute all that into our equation down here for displacement, then this actually means that d is equal to 0 too. And that makes it a lot easier, as we now have a full expression for the displacement, which is t squared minus ti plus 4t minus 3 over 2t squared j. So now we have our expression for displacement. We can find out what the displacement is at time t equals 4 seconds, because that's where point B is. So if we say that when t is equal to 4, and then we substitute in the numbers, 4 squared minus 4i plus 4 multiplied by 4 minus 3 over 2 4 squared j is actually equal to 12i minus 8j. So the displacement at the point B is 12i minus 8j. So if we were to draw a rough sketch of the points A and B, so if we say A is here, and we treat this as t equals 0, s equals 0, then from that, if point B is 12i, this means that it's 12 to the right, 12 along in the positive direction from A. And then minus 8j means that it is then 8 downwards in the negative j direction. So that means that it's 12 along and 8 down, and this is the point B when t is equal to 4. And that means that if we were to find the length of AB, we can just use Pythagoras' theorem, because we know these two lengths here, and this is a right angled triangle. So if we were to use Pythagoras' theorem to find the length AB, we would get that AB is equal to the root of 12 squared plus 8 squared, which actually is 4 root 13. And that is our length of AB. So we can say that the distance AB is equal to 4 root 13. And if we want to add a unit on, it's 4 root 13 metres. And there are 4 marks available for this question. Mark number 1 comes from integrating the equation for velocity to find an equation for the displacement, which we've done up here. And then we get a further answer mark for actually getting this correct. So we actually get 2 marks for integrating S. So just doing it at all and then getting the correct numbers they have in the mark scheme. Thirdly, we get a method mark for using Pythagoras' theorem to find the length AB, which is what we've done here, doing the root of 12 squared plus 8 squared. And finally, we have an answer mark for finding that this is the distance, 4 root 13 metres. 2 blocks A and B of masses 2m and 3m respectively are attached to the ends of a light string. Initially, A is held at rest on a fixed rough plane. The plane is inclined at angle alpha to the horizontal ground, where tan of alpha is equal to 5/12. The string passes over a small smooth pulley, P, fixed at the top of the plane. The part of the string from A to P is parallel to a line of greater slope of the plane. Block B hangs freely below P, as shown in figure 1. The coefficient of friction between A and the plane is 2/3. The blocks are released from rest with the string taut and A moves up the plane. The tension in the string immediately after the blocks are released is T, and the blocks are modelled as particles and the string is modelled as being inextensible. Part A asks us to show that T is equal to 12 mg/5. So the first thing we want to do for a question like this, where we've been given a lot of information, is it's very helpful to draw it onto the diagram so we can try and visualise it. So first of all, we're told that A and B have masses 2m and 3m respectively, and we can use this to find their weight, because force is equal to mass times acceleration, and we can assume that the acceleration on these blocks is gravitational acceleration, which we can call g. So if the mass is 2m, for example for A, if mass is 2m and acceleration is g, then the weight is 2mg. So if we drew this as an arrow acting vertically downwards, because that's the direction that weight acts in, we have a weight of 2mg for block A and a weight of 3mg for block B. Now on block A, we can also add what is called a normal reaction force, which is the force that acts at 90 degrees to the plane, and we can call it R, reaction force, and that's just kind of an opposition to the weight. Now, we're also told that the coefficient of friction between A and the plane is 2/3. So we can say that the frictional force on A, if we just call it F for now, we can work out what that is later. And finally, we know that the tension in the string after the blocks are released is T, and tension acts in these directions, like acting towards P, and we can call both of these T. And we know the tension on either side of the pulley is equal, because we're told right at the end that the string is modelled as being inextensible, and the main assumptions we can make from that is that the tension remains the same on either side of the pulley, and so does the acceleration, which is something that we'll need to know later on. So now we have all these forces marked on our diagram. The last thing we can do to do with annotating this diagram is we can actually take the components of the weight of A, this weight here, 2mg, because that makes it a lot easier when we want to resolve later on, as we'll need to resolve in this direction and this direction, and this weight does not act in either of these. So if we resolve it acting perpendicular to the plane, we know that weight acts still downwards, and resolving parallel to the plane, it must be acting this way, as that's kind of the direction the weight is pulling it in, if you like. So to resolve them, what we do is that we know this angle here is equal to alpha. So if this is alpha, then we can use trigonometry to find what the two sides are. So this one here, acting perpendicular to the plane, is adjacent to the angle alpha, and 2mg is the hypotenuse. So we can use the cosine rule to say that this is 2mg cos alpha. And we do the exact same thing for this component here to say that this is 2mg sine alpha. And now we have these, we can start to do some calculations. So the first thing we want to find is the reaction force that acts on A. So this one we've called R up here. And the reason for that will become a little clearer later on, but essentially it will help us find T because we can use R to find our frictional force. So to find R, what we want to do is resolve in the direction of R, which is kind of upwards and to the left in this kind of direction. And if we resolve upwards, we know that the only force acting, so this is using the equation F equals ma to solve these. So in terms of forces, the force acting in this direction, there's only one of, and that is R. And the force acting opposite to this direction is this component of the weight here, which we have said is equal to 2mg cos alpha. And now we know that because force is equal to mass times acceleration, this is our net force acting in this direction up, in the direction of R. And so if this is our force, we know that the mass of A is 2m. However, we know that the acceleration moving in this direction is 0 because the block is not moving upwards and to the left. And so we know that the acceleration is 0, and therefore m times A is 2m multiplied by 0, which is 0. So then if we add 2mg cos alpha to both sides, we know that the reaction force on A is equal to 2mg cos alpha. So now that we have this information, we can start to make what are called equations of motion for A and B, but R will help us with the equation of motion for A. So an equation of motion just means that we resolve in the direction that the block is moving, which for R is in this direction, kind of towards P, and B, it's downwards, vertically downwards. So if we start with A, and we say for A, and then as we're resolving in the direction that A is moving, and A is moving in this direction, we resolve this way, and then we go back to look at the diagram to see which forces act where. We know that the force, the only force acting in the direction of motion of A, is this one here, the tension force, which we've shown is acting that way with the arrow. And then there are two forces acting against this motion, the frictional force, which we've called F, and the component of weight here that we've called 2mg sine alpha. So again, using the equation F equals ma, we know that the force acting in this direction is T, and the forces acting opposite to this direction are F and 2mg sine alpha. And now this time, we can't say that it's equal to 0 because we're moving in the direction that of motion of A. So A does not have an acceleration of 0, but we do not know what this acceleration is. So if we just call it A, we know that the mass of A is 2m. So we have 2ma, mass times acceleration. Now what we want to do with this equation is try and simplify it a little bit, or as much as we possibly can. And the first way we can do this is by focusing on our F term, the frictional force that acts opposite to the motion of A. And the way that we can replace this with something else, to put it that way, is because we know that, and we're told in the question, that the coefficient between A and the plane is 2/3. And there's actually an equation that links the frictional force with the coefficient of friction, which is that frictional force is equal to mu, which represents the coefficient of friction, times by the reaction force, the normal reaction force. And therefore we can say that in our case, this frictional force is equal to 2/3 of R. And we know what R is, as we worked it out here. We know that for block A, R is equal to 2 mg cos alpha. So we can actually say that T take away 2/3 of R, where R is 2 mg cos alpha, take away 2 mg sine alpha, is equal to 2 ma. So we've gotten rid of a term now, the f, which should make it easier for us to solve. Now, we can go further with this, and the first way we can do this is using some more information we were given, which is that tan alpha is equal to 5/12. And what this means is if we were to draw out a right-angled triangle, where we can pick any angle to be alpha, so if we say this one, we know that tan alpha is 5/12, and since in general tan alpha is opposite over adjacent, we know that the opposite must be 5 and the adjacent 12, because then we'd get opposite over adjacent being equal to 5/12. And now we have these two numbers, we can use Pythagoras' theorem to find the length of the last, the hypotenuse of this triangle. So the square root of 12 squared plus 5 squared is equal to 13. So now we have this right angled triangle that we can use to find values for tan alpha, sine alpha, and cos alpha. So we know that tan alpha is 5/12, and we also know that since cos alpha is adjacent over hypotenuse, here we can see the adjacent is 12 and the hypotenuse 13, so it's equal to 12/13. And using the same method for sine alpha, opposite over hypotenuse, we have 5/13. And now we have values for all of these. We can use them to replace the cos alpha we have here and the sine alpha we have here. So if we do this and do a little bit of simplifying along with it, we have that T take away 2/3 of, and then 2 mg multiplied by 12/13. So 24/13 mg, and then take away 2 mg multiplied by 5/13, so 10/13 mg is equal still to 2 ma. And then if we expand out this bracket here and actually do the calculation, we're left with T take away 2 mg is equal to 2 ma. So now we have this expression for the tension in A, along with an m and an a term, which is why we can't solve this. We can do the exact same thing for B. So if we go back and look at the block B, we know that B moves vertically downwards in this direction of this arrow here. And so the forces acting in that direction are just the weight, 3 mg. And the force acting opposite to this direction, because there is only one, and that's the tension. So for F equals ma, when we resolve downwards, we know that 3 mg, take away the tension, is equal to mass times acceleration, where mass is 3m, and acceleration is again a. And the reason, this is all for B, and the reason we know that we can call this acceleration a when we also call the acceleration for a, is because we're told in the question that the string is modelled as being inextensible. And what inextensible means, or the assumptions we can make from that, is that the acceleration on either side of the pulley is the same, or the acceleration on both sides of the string is the same. And therefore the acceleration for A and B is equal, and so we can denote both with this same A. So now, given that we have this equation for A and for B that all have the same kind of terms in them, an M, a T, and an A, same unknown terms, I should say, what we want to do is make a simultaneous equation out of these two and solve. And because in the question we want to show that T is equal to 12 mg over 5, we know that in our final answer we're going to need a T and an M, but you'll notice there's no A which means we kind of want to cancel out these a's that we have. And so the way we can do that is substitute something in for a. So if we were to rearrange our equation for b a little bit, just by dividing everything by 3m, and then we're left with a is equal to 3mg take away t, all divided by 3m. And then we can substitute this in to the equation for a. So if we call this equation 1 and this equation 2, and we say that we want to substitute equation 2 into equation 1, then we end up with t take away 2mg is equal to 2m multiplied by a, and where we've replaced a with 3mg take away t divided by 3m. So now if we simplify the right hand side a little bit, we are left with 6m squared g minus 2mt, but because divided by 3m, but because we have an m in all of the terms on the numerator and the denominator, we can divide everything through by m, which simplifies then to 6mg take away 2t, and then this is all divided by 3. And now, if we times both sides by 3, we're left with 3t minus 6mg is equal to 6mg take away 2t. And so if we want to bring all the t's on one side and the everything else on another side, if we add 2t to both sides and then add 6mg to both sides, we get t's on the left hand side. So we have 5t is equal to 12mg. And then if we divide both sides by 5, we're left with t equals 12mg over 5, which is the form that the question asks for us to give tension in. Now, this is quite a long question. It's worth 8 marks. So our first mark comes from finding the reaction force, so stating that R is equal to 2mg cos alpha. That's our first mark. And then we get a further mark for somewhere saying that the frictional force is equal to 2/3 of R. So we've done that many places, as we've implied it in this formula by substituting it in here, and we've also stated it up next to here. So if we get a mark for that, if we just put it around where we've done that, and then we get 2 marks for writing an equation for A, because we get a method mark just for trying to write an equation of motion for A, and then we get another mark for actually getting it correct and writing the right equation. So if we get 2 marks for doing all of this, and then we get another 2 marks for doing the exact same thing for B, so attempting to write an equation of motion at all, and then getting the correct one. So this is 2 marks also. And then our next mark comes from writing out our full workings to find an equation in terms of T, M and G only, which means it implies that they want us to substitute something in for A to get rid of A, which is what we've done all down here. So that's our last method mark over here. And finally, we get our last mark for just showing that T is equal to 12mg divided by 5, so ending up with that at the end of our workings, which we've done down here. After B reaches the ground, A continues to move up the plane until it comes to rest before reaching P. Part B asks, determine whether A will remain at rest, carefully justifying your answer. So we know that the 2 options of what A can do once it's reached P is it can either remain at rest, which is what we're told in the question, or it can move down the plane. And the reason it can't move up the plane is because we're told it reaches P. So if it's right up by P, it can't move any further, which means it has to come down the plane again. And the reason this is important is it affects the way that the friction will act. Because if the block is now moving down the plane, hypothetically, if it were to move, then it would be moving down the plane, which would mean the frictional force no longer acts in this direction, but it acts in this one instead, acting kind of towards P. And the reason that's important is because if we were to draw a diagram of the forces that act on A at this point, so when A has reached P, if we were to draw A as this block here, then the weight is naturally going to be going this way, which is down the plane, because weight will always act this way regardless of which way A is moving, and therefore the component of the weight that acts parallel to the plane, 2mg sine alpha, will always act in this direction. So this is 2mg sine alpha, because that's the component of the weight that acts in this direction parallel to the plane. And as mentioned before, the frictional force now no longer acts in the same direction as the weight, but actually acts in the opposite direction because of the fact that A is either at rest or is moving down the plane as opposed to up. So we can now say that the frictional force is acting in this direction instead. And the frictional force, although it's acting in a different direction, it is the same value as it is before, which means it is 2/3 of the reaction force, so 2/3 of 2mg cos alpha. Now, if we actually solve what these are using the triangle from before, that had the sine alpha cos alpha on it, then we know that 2mg sine alpha is equal to 10mg over 13. And if we do the same thing with the frictional force, we know the frictional force is equal to 16mg over 13. And if we look at these two values, we can see that this force over here, 16mg over 13, is greater than the component of the weight, 10mg over 13. And if the frictional force is greater than the gravitational force, that means that the force acting upwards is greater than the force pulling it down, and therefore A will remain at rest because it's kind of keeping it in place. So the way we'd write this is that 16mg over 13 is greater than 10mg over 13, and therefore we know that the frictional force is greater than the gravitational force, and then we can just conclude that therefore A will remain at rest because the frictional force is kind of keeping it in place, and as it's greater than the gravitational force, it's not kind of allowing the block A to be pulled down the slope. And this will get us both marks for this question, because our first mark is a method mark for stating this fact here. So this will get us both marks for the question. Our first mark is a method mark, and it comes from here, just stating that 16mg over 13 is greater than 10mg over 13. So essentially saying that the frictional force is greater than the gravitational force. And then we get an answer mark for concluding that A won't move, A will remain at rest, which we've written in this sentence here. So part C is now asking us to suggest two refinements to the model that would make it more realistic. So essentially, if this model was in real life, what were some assumptions we made that we couldn't make in reality? So one of these could be the fact that we were told to assume that this pulley, P, was smooth. Smooth meaning it has absolutely no friction. And the problem with this is no object can be completely smooth. Everything has at least some kind of friction, even if that's a tiny amount. Nothing is completely smooth. And that was just an assumption that we made that allowed us to carry out calculations a bit easier, because it's just one less thing to take into account. So one refinement could be that we have to assume pulley is not smooth, or we can say that that means that it's rough, which is the opposite of smooth. Now, another assumption that we made that in reality we could not make is the fact that the string has no mass. We were told to assume it was light, so it has no weight and therefore no mass. But even if it's a tiny bit, all strings will have some kind of mass. Again, that was an assumption we made that made the calculations a bit easier. But in reality, we couldn't assume that this string was light, because that would mean no mass, which isn't very realistic. So we could say that we should also, to make it more realistic, we should assume that string isn't light and has mass. And now there are 2 marks available for this question, and they very simply come from suggesting 2 refinements. So it's a mark per refinement. So this would get us 1 mark, and this second one would get us another mark. But the mark scheme lists 4 different things. So it has these 2, and as well, the fact that we had to assume the string was inextensible was not a very realistic assumption. So refining this would make it more realistic. And another one was to talk about some of the dimensions of the blocks. So things like don't model them as particles or include the air resistance and things like that. That was another point that they mentioned would get you a mark. So there were a number of different things. It didn't have to be these 2 that you could put. These are just 2 examples that we could have had, but any of those ones I've just mentioned would get you 2 marks, as long as you list 2 separate ones. A ramp AB of length 8 metres and mass 20 kilograms rests in equilibrium with the end A on rough horizontal ground. The ramp rests on a smooth, solid cylindrical drum, which is partly under the ground. The drum is fixed with its axis at the same horizontal level as A. The point of contact between the ramp and the drum is C, where AC is equal to 5 metres, as shown in Figure 2. The ramp is resting in a vertical plane, which is perpendicular to the axis of the drum, at an angle theta to the horizontal, where tan of theta is equal to 7/24. The ramp is modelled as a uniform rod. Part A asks, explain why the reaction from the drum on the ramp at point C acts in a direction which is perpendicular to the ramp. So essentially, it is asking us why this force between the drum and the ramp here acts in kind of this direction, where this is a right angle. And the main kind of reason as to why is given to us in the question, because we're told that the drum is smooth, and smooth means no friction. So there is no friction between the ramp and the drum at the point C, and therefore there's no force to kind of disrupt the fact that the normal reaction force acts perpendicular to the plane. So because there is no friction, and because the drum is smooth, there's no friction, and therefore the reaction has to be perpendicular to the ramp. And that's all we need to write to get our 1 mark, because it's only a 1 mark question, so we don't need to write lots, just a sentence to say that the drum is smooth, and therefore the reaction is perpendicular to the ramp. And this will get us the 1 mark for the question, because that was all we needed to state was that because the drum was smooth, or you could have said no friction, either works because they mean the same thing. Because it's smooth, the reaction is perpendicular to the ramp. Now part B is asking us to find the magnitude of the resultant force acting on the ramp at A. And now, as you can see, this is quite a large question. It's worth 9 marks. So it might be worth drawing some of this information we've been given onto the diagram so we can kind of visualise it a bit better when it comes to answering the question. So the first thing we're told is that the ramp has a mass of 20 kilograms, and using the equation F equals ma, force equals mass times acceleration, we know that when the force is weight, the weight must be 20 kilograms times the gravitational acceleration, and therefore the weight of the ramp is 20g. And the way we can figure out where this weight acts, because it has to act somewhere along this ramp, is we were told that the ramp can be modelled as a uniform rod. And what this means is that this weight will act in the centre. The centre being 4 metres in, as we're told that the ramp has length 8 metres. So the centre of that is 4 metres in. So if we say that this is around 4 metres in, and we draw the weight acting vertically downwards, the weight being 20g. So that's the first thing we've drawn on, the weight of the ramp, as we know it acts in the centre. Now, the next thing we're told is that the ground is rough horizontal ground. And rough means that there is a frictional force. So we're being told here that there's a frictional force between the ramp and the ground. And the frictional force will act in, kind of towards the drum. So if we call that F, just for frictional force, that's another force we've added. And we also know that because of this, because the ground is rough, there must also be a reaction force acting perpendicular to this. And if we call this RA, meaning the reaction force at A, and the reason we need to say RA is because there's another reaction force, which is the one at C, that we were using in part A. So if we now call this RC, we have two reaction forces, and they're both perpendicular to the respective planes. This one is perpendicular to the ramp, and this one to the ground. Now, these are all the forces that we've been told about, and we've marked them all on the diagram. But there's one more thing that we can add that will help calculations in a minute, and that is if we componentize some of these forces, some of these forces being the RC and the 20G force. And the reason we want to do this will become a bit more apparent later, but if we want to be resolving vertically and horizontally, or kind of respective to this ramp, we'll need them to be resolved. So if we start with this weight, resolving would be perpendicular to the plane, which we can say is this line here. Not very accurate, but if this is perpendicular to the plane and this is parallel, we know that the one that's perpendicular is acting away, and the one that's parallel is kind of acting towards the way the weight acts. We know that this angle here must be theta, and therefore this component here would be 20g cos theta using trigonometry rules, and similarly this one is 20g sine theta because we're using the opposite and the hypotenuse, and for this one we were using adjacent and hypotenuse. And now if we do the exact same thing with RC, but this time we're resolving vertically and horizontally, whereas before we were resolving kind of in terms of the ramp. So if we first resolve vertically, we know that this is acting upwards, and horizontally will be acting again kind of towards the way that RC is acting. We know that this angle here must be theta again, because of kind of rules of angles, and therefore if this is a right angled triangle, this must be RC cos theta, and this one up here is RC sine theta. And I should also add that this weight acts 4 meters, kind of from A and from B, but we don't need to mark it on twice. So now that we have everything that we possibly could labelled on this diagram, we can now start to do some calculations. And the first calculation we can do, and this calculation will help us find the value of RC, is if we take moments about A. Because if we take moments about A, that eliminates this force and this force, because if we're taking them from this point, the distance to both of these is 0. Hence, the forces are kind of eliminated from the calculation. So if we take moments about A, and we want to do this clockwise. So we can denote that with this kind of arrow. Firstly, we want to find the forces that act kind of clockwise from the point A. And there's only one force that does this, and that is the weight. But we don't just want to use the weight, we want to use the component of the weight that acts perpendicular to the ramp. And that is because for moments, it's the distance multiplied by the force when it acts perpendicular to, in this case, the ramp. So because the equation for moments is the distance, which here is 4 meters, multiplied by this perpendicular force, we can say that the distance is 4, and then the force is not just 20g, but it's the one that acts perpendicular, which is 20g cos theta. And now this is the only force that acts clockwise to A, and the force that acts anti-clockwise to A, again, there's only one of, but this time it is RC, and it's not a component of RC, because if we look, we can see that RC is perpendicular to this ramp. And we know that RC is 5 meters away from the point A, so the distance, and we're taking this away because now this is anti-clockwise, the distance is 5 meters multiplied by RC. And we know that this is equal to 0, and the reason for this is because we were told that this ramp and everything rests in equilibrium. And one of the conditions of equilibrium is that the moments about a point are equal to 0. And so we can say that these moments have to be equal to 0. So if we do this calculation and add 5RC to both sides, we're left at 5RC is equal to 80g cos theta, and therefore RC is equal to 16g cos theta. And we can actually simplify this a little bit more because we can find out the value of cos theta. And the way we can do this is using the fact that tan theta is equal to 7 over 24, which is something we were told in the question. And that means if we were to draw out a right-angled triangle and called one of the angles, say this one, theta, we know that in general, tan theta is opposite over adjacent. And therefore, if it's 7 over 24, we can say that the opposite must be 7 and the adjacent must be 24. Because if we did opposite over adjacent here, we'd have that tan theta is equal to 7 over 24. So now that we have this, we can use Pythagoras' theorem to find this last length here, the hypotenuse, and we find that this is equal to 25. So now we can use trigonometry to find out an expression for tan theta, cos theta, and sine theta. So we can start off with the one we know, which is that tan theta is equal to 7 over 24. And now if we did cos theta, in general, cos theta is equal to the adjacent over the hypotenuse. And here we can see that adjacent is 24 and hypotenuse is 25. So cos theta is equal to 24 over 25. And if we do the exact same thing with sine theta, which is opposite over hypotenuse, we're left with 7 over 25. So now that we have all these expressions, we know that 16g cos theta is the same as 16g multiplied by 24 over 25. And if we put that in to our calculator and solve it, we can find that RC is equal to 384. So if we put that into our calculators and solve, we can find that RC is equal to 384g divided by 25. And if we just keep things in terms of g, it kind of prevents us from having long decimals that we need to write out, and we can just solve properly kind of at the end of the question. So now that we know what RC is, we can resolve upwards, vertically upwards, and horizontally to find RA and F. and that's because RC was the only unknown that was kind of stopping us from finding this. So if we start off with resolving upwards, which is in the direction of RA, if we resolve upwards, we know that the forces acting in this direction, upwards, are RA, as you can see here, and also this component of RC, which is RC cos theta. So we know that acting upwards, we have RA plus RC cos theta. And now we know the things that are acting downwards opposite to this. There's only one, and it is the weight here, which is 20g. So we can take 20g away for kind of the net force. And now this is based off the equation F equals ma. But because we know this whole system is in equilibrium, we know that acceleration is 0, and therefore this is equal to 0. And now we can do this calculation now because we know what RC is, as we've just worked out to be 384g over 25. And we know what cos theta is, as it's 24 over 25. So now we can be left with RA plus, and then RC cos theta, if we do 384g over 25 multiplied by 24 over 25, we're left with 9,216g divided by 625, and then this is still take away 20g is equal to 0. And now if we add 20g to both sides and take away 9,216g over 625, we are left with RA is equal to 3,284 g over 625. And now, if we do the exact same thing, resolving horizontally, kind of to the right in this diagram, which is in the direction of F, we can do the exact same thing to find an answer for what F is. So if we resolve horizontally, we know that the forces acting in this direction are just F. F is the only force acting in this direction. And then the forces acting in the opposite direction, again, there's only one of, but this time it's this component of RC, which is RC sine theta. So resolving horizontally, we know that we have F take away RC sine theta. And again, for the same reason as before with the F equals ma, where this is in equilibrium, so acceleration is 0, we know that this equation is equal to 0. And now, we know that RC sine theta is equal to 384g over 25 multiplied by 7 over 25. So we can say that this is equal to F minus 2,688g over 625 is equal to 0. And therefore, if we add that to both sides, we get that F is equal to 2,688g over 625. So now we have values for RA and F. So if we were to draw this triangle out where we know that RA acts upwards like this and F acts horizontally like this, the question originally was asking us to find a value for the resultant force acting on the ramp at A. And the way we can draw that is it's the resultant force of these two forces. And so the way we can find this is using Pythagoras' theorem, because if we were to draw this triangle another way, we could draw it as the resultant force being this line, the hypotenuse of these two forces. And so using Pythagoras' theorem, we get that the resultant is equal to the square root of RA squared plus F squared. we know that RA is equal to 3,284 G over 625, and then that's squared, plus F, which we've just found out to be 2,688 G over 625 squared. And then if we do that in our calculator, we find that the resultant force to 3SF is equal to 66.5 newtons. And now this question was worth 9 marks. So if we go back to look where these all came from, we get a total of 6 marks for these first 3 equations that we constructed for the moments about A and then resolving vertically upwards and horizontally. And the reason we get 6 marks for that is because you get a method mark and an answer mark for each one. So kind of attempting to do it and then doing it correctly will get you 2 marks for each equation. So constructing this equation here gets us 2 marks. Constructing this equation here gets 2, as does this one. So it's a method mark and an answer mark for each. So our next 3 marks now come from, first of all, finding a value for RA, so the reaction force at A, and F, the frictional force. So getting this value and this value will get you 1 mark for getting both of them. So if we mark that on here. And now next, our second to last mark comes from over here using Pythagoras' theorem to find the resultant force. So just doing that the resultant force is equal to the square root of r squared plus f squared, as they say in the mark scheme, is 1 method mark. And finally, we get an answer mark for finding that the magnitude of the resultant force is 66.5 newtons to 3SF, or you can also give it to 2SF if you want, but either gets you the final 9th mark. So we're now told the ramp is still in equilibrium in the position shown in figure 2, but the ramp is not now modelled as being uniform. Given that the centre of mass of the ramp is assumed to be closer to A than to B, Part C asks to state how this would affect the magnitude of the normal reaction between the ramp and the drum at C. So first of all, if we're told that the centre of the mass is assumed to be closer to A than B, if we were to draw that on the diagram, it would look something like here, for example. It could be any place less than where it previously was, which was 4 meters kind of along. So if this was where it used to be, and we've now moved it closer to A than it is to B, then we know that this is now the centre of mass, where the centre of mass acts. And if we were to now take moments about A, like we did in part B, so our first step in part B was to take moments about A. So if we were to do this now with our moved centre of mass of the ramp, we would notice that the clockwise moment about A would decrease, because when we were taking moments about A, the only thing that had a clockwise moment was this centre of mass force, and the only thing that had an anti-clockwise moment was this reaction force at C, if we just label that on the diagram here. And so, given that moments are the distance multiplied by the force, if our distance between A and this point here has decreased, then the total moment of this force will decrease. And if this is the only clockwise moment acting, then the clockwise moment about A will decrease. And since we had it's the clockwise moment take away the anti-clockwise moment is equal to 0, if the clockwise moment decreases, then so will the anti-clockwise moment. And what this means is that the magnitude of the normal reaction at C will decrease, because that's involved with the anti-clockwise moment, and if one decreases, the other does. And so we can say that the magnitude of the normal reaction at C will decrease. And for this question, because it is simply state how this will affect the magnitude of the normal reaction, we don't actually have to give a reason why. It is literally asking us to say whether it would increase, decrease, or stay the same. And so this is enough to get us 1 mark, because we've stated that it will decrease, and that is the answer. The points A and B lie 50 metres apart on horizontal ground. At time t equals 0, 2 small balls, P and Q, are projected in the vertical plane containing AB. Ball P is projected from A with speed 20 meters per second at 30 degrees to AB, and ball Q is projected from B with speed u meters per second at angle theta to BA, as shown in figure 3. At time t equals 2 seconds, P and Q collide. Until they collide, the balls are modelled as particles moving freely under gravity. Part A asks, find the velocity of P at the instant before it collides with Q. So the first thing we want to do on a projectile motion question like this, where we have two speeds at angles to horizontal ground, is it's actually quite helpful for us to resolve these into horizontal and vertical components, because when it comes to doing calculations a little bit later on, they become much easier when we have horizontal and vertical components as opposed to ones at these angles. So if we start by doing this, we focus on P. If we do the vertical component, we know it's going upwards, as that's kind of the general direction of P. It's going upwards. And then we can use trigonometry to say that if this is the hypotenuse and this is the opposite, that this is therefore equal to 20 sine 30. As we did, sine 30 is equal to the opposite over 20. If we rearrange that, we get that it's equal to 20 sine 30. And then if we do the exact same for the horizontal, but this time we have the hypotenuse and the adjacent, we know that this is then 20 cos 30. And now if we do the exact same thing using the same method for Q, we know that vertically it's still going upwards, but this time it's u sine theta, and horizontally it's u cos theta, so it's the same as what we did for P, just replacing 20 with u and 30 with theta. So now we've marked this onto our diagram. If we look back at the question asks us to find the velocity of P, so we know we're going to be focusing on P over here, and we want to know the velocity of P just before it collides with Q. And we're also told in the question that they collide at t equals 2 seconds. So we're probably going to need to include that somewhere in our calculation. So we know for a question like this, projectile motion questions often use the constant acceleration formula, sometimes called the Suvat equations. So if we were to start by forming one of them when resolving vertically, but we could do horizontally first, it doesn't really matter. But if we start by resolving vertically upwards, and this is all for P, and we write out all the terms that could possibly be in any of the 5 Suvat equations, and then we can just kind of fill in the ones that we know. So S is displacement, and now we're not told anywhere in the question what the displacement of P is at any point, and we're not trying to find it either. So we can say that S we don't know, we can put a dash there to say we're almost ignoring it. Now U is the initial velocity, and the initial velocity when resolving upwards is this here, which we found to be 20 sine 30. So we can say that U is equal to 20 sine 30. And V, we don't know what V is, because V is the final velocity of the particle P in this case, and we've not been told what this is. But what we do know is that this is what we're trying to find, because the question is asking us to find the velocity of P. And what this V is the vertical component of this velocity just before it collides with Q. And so since this is only the vertical component, we can't just call it V, because we're going to need to be finding another velocity, so we can find the final one, which we can call the resultant of these two forces. So if we call this V1, so meaning it's the vertical component of the final velocity, and now we need to find A, and although we've not explicitly been told a value of A, we have been told that until they collide, the balls are modelled as particles moving freely under gravity. And what freely under gravity means is that the acceleration when they're moving vertically is g, which acts downwards, gravity acts downwards. So when we're resolving downwards, we can say that the acceleration is equal to g. And now, since we're resolving upwards, the opposite of that would be minus g. So the acceleration of p is minus g, and g has a value of 9.8 for questions like this. But if we leave it as g, we can substitute that in later. And last but not least, we have t, and we're told in the question that they collide when t is equal to 2 seconds, and we want to find the velocity of p at this instant, just before that. So we can say that t is equal to 2. So now we have values, or an unknown, for 4 of these 5, and there is one equation that kind of fulfills this, so it doesn't have an s in it and it has the rest of them, and that equation is v equals u plus at. So if we write that here, we can say that v is equal to u plus at, and so if we substitute in the values, we know that v is equal to v1, u is equal to 20 sine 30, and then plus at is the same as minus g multiplied by 2. And if we put this into the calculator, we say that therefore v1 is equal to minus 9.6, and that's minus 9.6 resolving upwards, which means that resolving downwards it's just 9.6, and this is a velocity, so it's in meters per second. So now we have the vertical component of the velocity. What we now want to do is find the horizontal component of the velocity. So if we do the exact same thing and resolve horizontally in the direction that the ball moves, and do what we did before with the s, u, v, a and t, we still don't know the displacement. The initial velocity is now this horizontal component of the initial velocity, which we found to be 20 cos 30. We still don't know the final velocity, but again, it's what we're trying to find. But this velocity is going to be different to this one here because this is now the horizontal component. So if we call this v2, just to kind of differentiate between this one and this one, because they are different, they will be different values. And now a, when resolving horizontally for projectile motion questions like this, we can actually say that a is equal to 0. There's no acceleration. And then lastly, t is again 2. This doesn't change depending on which way you resolve because time doesn't have a kind of direction, and p and q collide at t equals 2, so we leave that as it is. So now if we do the exact same thing, we have the same terms that we know and the same term s that we don't know, so we can use the exact same equation that we did previously, v equals u plus at, but now we have that if we substitute in, v2 is equal to 20 cos 30, and since a is 0, at is also equal to 0, and so we can leave it at 20 cos 30, and then we put this in a calculator to find that v2 is equal to 10 root 3 meters per second. So now what we have is the horizontal and vertical components of this velocity of p just before it collides with q. So if we were to draw this, we can say that v1 is minus 9.6, which means acting downwards it is 9.6, and v2 is just 10 root 3 positive, so we know it's acting in the direction we resolved in, which was this one. And since we want to find the velocity, just the velocity, not a component of the velocity, what we can do is say that that is the resultant of these two components. And another thing to note is that because we want to find the velocity of p, what this always means in a question like this, and they kind of hide it, but it's implied, is that we need to find the angle at which this kind of acts. So we need to find out what this angle here is below the horizontal. So if first of all we go to find the actual value of v, we can see that this can make a right angled triangle, because if this here is 9.6 then this here is also 9.6, this axe there. And therefore, to find the kind of resultant of these two forces, and we do Pythagoras' theorem, where we have 9.6 squared plus 10 root 3 squared, and then we can find that the resultant of these two is 19.8 to 3 SF, to 3 significant figures. So now we have the value of the velocity, but we still don't have the angle, and so to find the angle, if we use trigonometry, and therefore we need to use tan, because it's tan alpha equals opposite over adjacent. So if we write that out, where tan alpha is equal to opposite over adjacent, but we know that opposite is 9.6 and adjacent is 10 root 3. And so if we take the inverse of tan on both sides and put that into our calculator, we find that alpha is therefore equal to 29.0 degrees to 3 significant figures. So now we have a value for the velocity and the angle at which it acts below the horizontal. We can conclude to say that the velocity is equal to 19.8 meters per second to 3SF. And then we have to specify that it's at 29 degrees below the horizontal. It tends to be better to specify kind of where this angle is, whether it's below the horizontal, above it, just to be extra clear. So it's 29 degrees below the horizontal, and we know that because it's kind of shown here. And that's what we need to do to get 6 marks. So the first mark from this comes from actually stating that the horizontal speed is 20 cos 30, which we've done here, and we've also labelled it on our diagram a bit up. Second of all, we get a method mark for attempting to find the vertical velocity at t equals 2, which is what we've done here. And then we get a further answer mark for doing this correctly, which is what we've done here. So doing 20 sine 30 minus 2g, and then solving that. And now we get another method mark for finding the speed. You can do this using Pythagoras' theorem or trigonometry. We've done it here with Pythagoras' theorem, so that's another mark, just as a method mark for doing it at all, not for getting the answer. And then we get another mark for trying to find the angle using tan, which we've done up here. And now, last but not least, we get an answer mark for just finding that therefore the velocity is 19.8 meters per second at 29 degrees below the horizontal. So that's our last answer mark, and that's all 6 marks. Now B is asking us to find for part I the size of angle theta, and for II the value of u. Now this question, although it's split into I and II, it's quite joined. You need to find one to be able to find the other, so it's quite hard to separate this until we get to the answers into a part I and II, so we'll kind of be finding them at the same time. But the first thing we want to do is use what we already know, that P and Q collide when time is equal to 2 seconds. And therefore, if we think about resolving vertically, the vertical height of P at t equals 2 seconds must be the same as the vertical height of Q at t equals 2 seconds, because if they're colliding, they must be at the same vertical height. And similarly, since we know that this whole, from A to B, this whole ground is 50 meters, whatever height, whatever horizontal distance P is at when they collide, the distance of Q from B must be 50 minus that height, because we know that the horizontal distance of P from A to the point of collision plus the horizontal distance of Q from B to the point of collision must add up to make 50. And so we can use that information to find theta and u. And the way we can do that is, first of all, by finding what the vertical height and the horizontal distance of P is at this collision. because we have more information about P, because we know the velocity it's travelling at and the angle, which is what we don't know for Q. So if we start out for P, and if we start by resolving vertically, we know if we resolve up and do another Suvat equation like we did in part A, we know that although we don't know the displacement resolving upwards, it's what we're trying to find. So we can put a question mark for that. The initial velocity resolving upwards we found is this, which is 20 sine 30. And then the final velocity, we did find it in part A, but we don't actually need to use it because we can have one thing that we can say we don't know. And in an exam situation or answering this question, we don't actually know that part A is right, and therefore it's actually safer to say we don't know this. But we know that A must be minus G because we're resolving upwards vertically, and then T is 2 seconds because we're trying to find the displacement at the point of collision, which we're told is when T is equal to 2. So using this information, we know that the equation that doesn't have V in it but has the rest of these terms in it is S equals ut plus half at squared. It's one of the constant acceleration formula. And so if we substitute in the values we have, we don't know S, but we know u is 20 sine 30 and t is 2. So ut we can write as 2 multiplied by 20 sine 30. And then plus half, a is minus g, t is 2, so that's t squared. Now if we simplify this and put that into the calculator, we find that therefore s is equal to 0.4 meters. So at this point of collision, P, and therefore Q, is 0.4 meters above the ground. And so, since we know this, and therefore we've said that therefore Q is also 0.4 meters above the ground, we can do this and we can make this into an equation. So if we now move on to Q, but we do the exact same thing, just with different numbers, we know now that the distance at t equals 2 seconds is 0.4 meters. The initial velocity, if we go back to our model, we found when resolving upwards is this, which we found to be u sine theta. So we know that u is equal to u sine theta. V we don't know and don't need to know for this question. A is again minus g because both P and Q move freely under gravity, as we're told. And then since we're finding it at the point of collision, we know that t is equal to 2 seconds again. And now we know that the equation that doesn't have v in it is again s equals ut plus half at squared. But this time we know what s is, it's 0.4. ut is u sine theta multiplied by 2, which we can write as 2u sine theta. And now we have half at squared. And therefore, if we simplify this a bit further, we get that 0.4 is equal to 2u sine theta minus 2g. And now if we add 2g to both sides and then divide by 2, so we can have u sine theta by itself, we're left with u sine theta is equal to 0.2 plus g. And that's as far as we can simplify because we have two unknown terms, the u and the theta. And the way that we can find what these are is by now doing exactly what we've just done, but resolving horizontally. So if we start off again with P, because we know more values for P, and we resolve horizontally, doing Suvat again, we do not know the displacement, but that's what we want to find. We know that U is equal to 20 cos 30, as we found previously. V is not needed. A is equal to 0 because this is now horizontal, not vertical. and again, we want to know the displacement at the time of the collision, which happens when t is equal to 2 seconds. So it's the same equation as before. The one without v is s equals ut plus half at squared, and therefore s is equal to 2 multiplied by 20 cos 30, and then plus 0, because if a is equal to 0, half at squared is multiplied by 0 and therefore is 0 itself. And so we can say that s is equal to 20 root 3 meters. And now if we look back up at our diagram, we know that the distance between A to B is 50 meters. And so if A to the collision is 20 root 3 meters, the collision to B must be 50 take away 20 root 3. And so if we were to go back now and resolve, we want to resolve in the other way for Q, if we specify that this is for Q. We want to resolve in the other way just because that's the direction that Q moves, so it's easier, we don't have to make things negative or anything. We know that the distance is 50 take away 20 root 3. And now u is equal to u cos theta, and we can see that if we go back to our diagram, the horizontal velocity here, the horizontal component of the velocity is u cos theta. And now v is unknown again. A is 0 as it was for p, again because this is horizontal motion, and t is 2 because we want to find the velocity at the collision, at the point of collision, or rather we're using the displacement from the point of collision. And so it's the same equation as we've used for all the others, but now we substitute in s is equal to 50 take away 20 root 3, and this is equal to 2 times u cos theta, which we can write as 2u cos theta. And since a is 0, half at squared must also be 0 because we have something multiplied by 0. And therefore, if we divide this all by 2, so we can get u cos theta by itself, we have that u cos theta is equal to 25 minus 10 root 3. So now you'll notice we have two equations that have a u and a theta in them. And what this means is that we can do a simultaneous equation. So if we go back to our original equation with u sine theta, if we call this equation 1, and we call our one with u cos theta equation 2, we know that as a general rule, sine theta over cos theta is equal to tan theta. And since we have a sine theta and a cos theta, the best way that we can cancel these out so we can find theta to start off with is by using this. So therefore, if we divide equation 1 by equation 2, what we're left with is u sine theta over u cos theta on the left-hand side. And this is equal to 0.2 plus g divided by 25 minus 10 root 3. And since we have a u on the numerator and a u on the denominator, these can cancel out because u divided by u is 1. And as I said previously, sine theta over cos theta is equal to tan theta. So we can write this as tan theta equals 0.2 plus g divided by 25, take away 10 root 3. And now if we take the inverse tan of both sides, we're then left that theta to 3 significant figures is equal to 52.5 degrees. So now we've answered part I, so we could put this as part I. It's quite hard to differentiate, as I said previously, hard to differentiate between I and II, because now for part II, we need to use this value of theta. And so we can use either one of the two equations we found. If we just use u cos theta equals 25 minus 10 root 3, we know that theta is 52.5, And so we can say that u cos of 52.5, to 3 significant figures. Obviously, when doing this in your calculator, use the entire number. This is equal to 25, take away 10 root 3. And so if we divide both sides by cos of 52.5 and put this into our calculator, we find that u is equal to 12.6. This is to 3 significant figures. So this question, although there was a part I and II, the mark scheme actually doesn't differentiate between the two. So like where marks come from for either, for part I or II, they just list it as a question B. But first two marks come from finding the vertical distance for P, and then recognizing that it's equal to the vertical distance of Q, and therefore doing this equation. And we get 2 marks for this because we get a method mark just for kind of attempting this, or stating that we know that the vertical distances are equal regardless of what numbers you then find. So that's a method mark. And then you get a further answer mark for using the right numbers and getting this final equation for u sine theta. So if we say that that answer is 1 mark, and just doing this entire thing is another mark, so we get 2 marks for doing vertical distance, and then we get a further 2 marks for doing the exact same with horizontal distance, so stating that we know that the sum of the horizontal distances is 50, and therefore for Q, S is equal to 50 minus 20 root 3. That's a method mark, just for kind of showing that you know this fact. And then we get another answer mark for finding that, therefore, if we put in all the other numbers, u cos theta is equal to 25 minus 10 root 3. So that's now 4 marks out of 6. And then we get another mark for just solving for theta and u. And so just doing all of this working will get us another mark, and that's this working here and also this, but it's 1 mark for both, so if we just put it there. And then lastly, we get an answer mark for finding a value of theta and a value of u. So if we mark that on here, so finding that theta is 52.5 degrees and u is 12.6. So part C is asking us to now state one limitation of the model, other than air resistance, that could affect the accuracy of your answers. Now, the mark scheme actually gives quite a few different things that we could put, as well as stating that any factor that's relating to the model, as stated in the question, will get you a mark. So there's quite a big variety of things you can put. For example, that it doesn't take account of the fact that they aren't particles. So in the question, we were told to model the balls as particles, but in reality, they aren't. This is just an assumption we make that allows calculations to be done a lot easier, so we have less things to take into account. So that's one limitation we have. Another we could say is that it doesn't take into account the actual size of the balls. So how do we know that ball P isn't bigger than ball Q or vice versa? And that would, again, affect your answers if we were doing this in a more real-life situation. And there are 2 of many different things that we could have said. So we can say that the model doesn't take into account that P and Q aren't actually particles. And now this would get us the 1 mark needed for the question. And as I said previously, any valid answer referring to a limitation of the model would get you a mark.